All right, two main things to do today. That is to go over a couple of the exam problems, one being a problem about transformations and one being really, well, ultimately a problem about convolutions when you do it differently than the moment generating function technique. We'll talk about continuous convolutions today. We did discrete convolution last week. We'll do continuous convolution, the basic idea within the context of an example today. But let's start by looking at the take-home problem number one, which is a transformation problem and kind of a strange transformation problem. You might wonder whether it's got any applications. And certainly that's a good thing to wonder, but I thought it was interesting, and so I thought it was worth doing. And I thought it was also worth doing in the sense of showing you do have the capability of doing things like this, and I hope with enough direction like I gave you that you were able to all get it eventually. So X is a continuous uniformly distributed random variable on the interval from 0 to pi over 2. And we've got a transformation. Y equals h of x equals sine of x. So y is going to be a new random variable whose values that it can take on are the sines of the values that x can take on. So if x goes from 0 to pi over 2, you plug that in numbers like that into the sine function, you're going to get numbers out between 0 and 1. Okay, those are the possible values for y. Part A, as always, use the CDF method to show that the PDF has a certain formula. So let's confirm that. That hopefully was the easiest part of the problem. But you do need to figure out the CDF of x first. But being uniform, hopefully that wasn't too much of a problem. X is uniform on the interval from 0 to pi over 2. And it's okay if you just wrote down the CDF right away. But if you want to write down the PDF first, so piecewise function say, that means the PDF is going to be 2 over pi when x is between 0 and pi over 2. And 0 otherwise, I'll abbreviate otherwise as just OW. And that'll mean the CDF, capital F. Well, if you want to be extra careful about it, it's technically 0 if x is less than or equal to 0. 1, not 0, if x is greater than or equal to pi over 2. And it's the integral of 2 over pi with respect to x when x is between 0 and pi over 2. In other words, just multiply that by x. Should I add a plus c to integrate that when I integrate that? Should I put plus c in there? I hope you didn't. C is 0 because you want capital F of 0 to equal 0. That's why. And you want the right hand, you want it to be continuous in this case. You want the right hand limit as x approaches 0 to be 0. So this quantity needs to be something that goes to 0 as x goes to 0. So that's the CDF for capital X. Y is the sine of capital X by a transformation capital H. I called it capital H to kind of match the capital H in chapter 4 of the book in the expected value formula. Could have called it little h, but whatever. That's the sine of x. We want to find the PDF of y. Use the CDF method. First find the CDF of y and then differentiate it. As always, it's this. And yeah, this will be 0 when y is negative and will be 1 when y is bigger than what? Pi over 2? Go ahead and say it. 1 when y is bigger than 1. So this is only something interesting when y is between 0 and 1. Assume y is between 0 and 1 to make it interesting. I mean, yes, this equation still works right here when y is less than 0 and when y is bigger than 1. And I guess this equation still works there. But the next one, when I take the inverse sine of both sides in the inequality there, I really should be assuming y is between 0 and 1. Certainly not bigger than 1, because I hope you remember you can't plug something bigger than 1 into the inverse sine function, at least if you want a real answer. You actually can plug it into the inverse sine function when you allow complex numbers, strange as that may seem. Mathematica, what's the arcsine of 2? Approximately 1.57 minus 1.32i. Yeah, all sorts of weird things happen when you allow complex numbers. It's not a typo there. Anyway, for us, you can't plug something bigger than 1 into the inverse sine function. You can plug something between -1 and 0 into it. But as far as ultimately simplifying the way we want to, since x is between 0 and pi over 2, y is going to be between 0 and 1 anyway. So take the inverse sine of both sides. And the inequality does stay the same direction, less than or equal to. If you had to give a reason for that, do you think you could give a reason for that? Why does the inequality stay the same direction? Do you ever think about why? I mean, you know that when we multiply or divide by a negative number, you know the inequality changes direction. Why does it not change direction when we, for example, apply the inverse sine function? Anybody ever been told why or remember why? Has to do with the nature of the graph of the inverse sine function. It's always what? What's my hand doing here? It's always increasing. If you don't remember the graph, well, here it is. That's the graph of the inverse sine function. Its domain is -1 to +1. It's the reflection of a piece of the sine graph about the line y equals x. I'm not drawing the sine function, but maybe you can imagine it. And its outputs are between -pi over 2 and +pi over 2. Anyway, it is increasing, so the inequality can stay the same direction. And this is capital F sub x of the inverse sine of y. And I guess here's where I'm really using the fact that y is between 0 and 1 fully, in saying in that case, the inverse sine of y is between 0 and pi over 2, and therefore I can use this formula and get 2 over pi times the inverse sine of y. Y is between 0 and 1. It would be 0 when y is less than 0 and 1 when y is greater than or equal to 1. And little f is the derivative of capital F. And going back to your Calc 1 days, take the derivative of inverse sine, you'll get 1 over square root of 1 minus y squared. So you get the answer in the exam. It looks like that. Let's go ahead and use Mathematica to check that this does seem to be a PDF. It should integrate to 1, right? Oops. 2 over pi times the square root of 1 minus y squared. That's actually a pretty easy integral to do because antiderivative is going to be the CDF. Technically speaking, it's an improper integral. It's got an impropriety at y equals 1. Technically speaking, it's a limit of integrals that look like this when as b approaches 1 from the left. But those integrals, when you do them, all involve 2 over pi times the inverse sine of b. In fact, they equal 2 over pi times the inverse sine of b. Inverse sine of b as b goes to 1 from the left approaches pi over 2. 2 over pi times pi over 2 is 1. So technically it's an improper integral, but you didn't have to check this anyway. Oops. All right, so that is the answer for part A. Part B, show it worked by hand in two ways. That the expected value y is 2 over pi, first by doing an integral involving the PDF of x, and second by doing an integral involving the PDF of y. We're after the expected value of y. Based on the PDF of x, that means go back to chapter 4 and use the generalized expectation formula. The expected value of a function of a random variable. In this case, that's the expected value of the sine of x. Right? And the generalized expectation formula says to integrate whatever that function is, in this case, the sine of x, times the PDF of x. Over whatever the domain is for the PDF of x where it's positive. That domain is 0 to pi over 2. And the formula for the PDF when x is between 0 and pi over 2 is 2 over pi. So that's a 2 over pi. So you get 2 over pi times integrate sine, you're going to get negative cosine. So you get negative cosine of pi over 2 minus negative cosine of 0. Cosine of pi over 2 is 0. Cosine of 0 is 1. 2 minuses make a plus. 2 over pi is the answer. So that one's fairly easy to do, but you got to know what to do. You can also do it as an integral involving the PDF of y. This thing here. Integrate y times the PDF of y is what you should have done over the interval where the PDF is positive 0 to 1. This should give the same answer. But this was the one where I said, technically speaking, if you're going to be, well, you could do it just by guessing the antiderivative or figuring it out on the side. But if you're going to be careful about this as a definite integral, you should do a substitution. U or W equals 1 minus y squared is a good substitution to do. And dw is negative 2y dy, which is almost up there except for no minus sign. So it looks like we get negative 1 over pi. I brought the 1 over pi out, and I also brought a negative sign out. Ultimately, w to the negative 1/2 dw. You should change the limits of integration, though. You got to be careful when you do this. Use this equation here. When y is 0, w is 1 minus 0 squared is 1. And when y is 1, w is 1 minus 1 squared is 0. Huh. Is that wrong? No, that's actually right. However, you can switch them back to going from 0 to 1 and then just negate the negative sign to get a positive sign. This is the same as this. And yeah, this is still technically an improper integral. This is, this is 1 over square root of w. There's an impropriety and a vertical asymptote at 0. So technically speaking, it's a limit of proper integrals, but once again, you can do it without bothering to write the limit sign. And it works out pretty nicely. Integrate w to the negative 1/2, you get w to the positive 1/2 divided by 1/2. Dividing by 1/2 is the same as multiplying by 2. In the end, you get 2 over pi still. It's nice to see you get the same answer. So I hope with, me telling you what the answer was, that even if you were confused at first, you were able to figure this out. And it is confusing. It's all these different variables all over the place, you know, as part of the confusion. But if you go carefully and think about concepts and what we've learned, I hope most of you were able to get this. I would like to show you again a Mathematica animation that's going to illustrate this stuff pretty nicely. Let's keep going before we do that. Part C, find the mean and standard deviation. No, find the standard deviation. Any way you want, effectively. One way might be easier than the other. I was unsure if, when I was first writing this, I was thinking one way might be significantly harder than the other. But then I actually tried them both this morning, and one way is harder than the other because it just seems harder, but it's actually completely equivalent to the other way in terms of difficulty level because of a substitution you can do. It's just that the substitution is not so clear. Of course, to find the standard deviation, we got to find the variance first. And to find the variance, we got to find the second moment first. So you could find the second moment of y, which is the hardest part of the problem. And the way I was thinking of doing this that would be easier is to use the generalized expectation formula to say this is the same as the expected value of h of x squared. In other words, the expected value of sine squared x. And doing that integral, although that's still not super easy because you got to integrate sine squared. If you use the table or use Mathematica to do that integral, it's okay to a certain degree. Did I say by hand? I did say by hand. The integral ends up being the integral from 0 to pi over 2 of sine squared x times 2 over pi dx. That's the PDF of x right there. You can do this either by doing integration by parts a couple times, or it's okay if you look that up in the table, or use Mathematica to just do this integral symbolically, at least just if you start it by hand like this. I like doing it by using a trig identity. And this is what I teach my Calc 2 students if you're tutoring them in math lab. Sine squared x is the same as 1/2 minus 1/2 cos 2x. Just a trig identity to say those are equal. If it were cos squared x, by the way, this becomes 1/2 plus 1/2 cos 2x. That's the way I teach my Calc 2 students to do this one, because that's fairly easy to integrate. Integrate 1/2, you get 1/2 x. Integrate minus 1/2 cos 2x, you'll get minus 1/4 sine 2x. Sine of 2x evaluated at both 0 and pi over 2 is 0, right? Sine of 0 is 0. 2 times pi over 2 is pi, sine of pi is 0. So the sign here really doesn't affect anything. The only way you get something non-zero is when you replace x over here with pi over 2. So you get 2 over pi times 1/2 times pi over 2 is pi over 4. 1/2 is the second moment. Before doing the variance and standard deviation, let's think about the second moment with the other method. It looks harder, but it really ends up being equivalent if you do a trigonometric substitution. So if instead you do it using the PDF of y, kind of like this, except make a y squared there. Then you're integrating 2y squared over pi times the square root of 1 minus y squared. which looks really hard to do. And, an ordinary substitution that you might try, w equals 1 minus y squared, doesn't seem to help much because it's a y squared up there. But a trig substitution is the way to go here. I don't know if you remember trig substitutions from Calc 2. If you're a tutor in math lab, you may have helped some students do them. Let y, because of the square root of 1 minus y squared here, it's a good idea to let y equal, say, sine theta. I'll use a theta. I could have used an x. dy is cos theta d theta. The y squared up there can be replaced with sine squared theta. The y squared in here gets replaced with sine squared theta. And then dy gets replaced with cos theta d theta. Do need new limits of integration, use this equation. When y is sine theta, theta is inverse sine of y. So when y is 0, theta is the inverse sine of 0, which is still 0. But when y is 1, theta is the inverse sine of 1, which is pi over 2. This is starting to feel familiar. It simplifies things. Once you do the trig substitution, they're equivalent in difficulty. That's a cos squared theta. Technically, the square root of cos squared theta is the absolute value of cos theta. However, theta is between 0 and pi over 2. So cos theta is positive. So this is the same as cos theta. And that means the cosine theta there cancels with the cosine theta there. And yeah, I'm doing the exact same integral as before. Integral from 0 to pi over 2 of 2 over pi sine squared theta. It's the exact same. You get 1/2. Sorry. It's nice to see it work out. I'm expecting most of you did it this way. And maybe you used integration by parts, or if you use the table or Mathematica to do the antiderivative, that's fine. Right here with this sine 2x, you may have gotten 2 sine x cos x instead, because that's a trig identity. You may have gotten that. Maybe doing integration by parts twice gives you that. 2 sine x times cos x. You still get the same answer. So the variance then becomes the second moment, 1/2 minus the first moment squared. The first moment was 2 over pi, right? So that'll be 1/2 minus 4 over pi squared. Get a common denominator of 2 pi squared. And there we go. The standard deviation is what it says is the square root of that. And that can be written as I have on the paper, square root of pi squared minus 8 divided by square root of 2 times square root of pi squared is pi. Then you simulate it. So let's look at Mathematica now. So I'm using random variate to do the simulation. Did I say 100 data points? Sample size 100. To get the y data, the transform data, you can map the h function onto the x data. I add a little bit more in here just to see. Ignore this at the moment. just to see a graph of the X data. Fairly uniform. What about the Y data? I didn't require you to do this. Not as uniform, though it's not completely obvious that it's not as uniform. They both look relatively uniform. But the Y data, technically speaking, is going to be denser over here. Let's try to rerun the simulation and see if it's more obvious. Okay, there it's seeming fairly obvious that the data is pretty dense over there when the Y is close to 1. And the PDF of Y gets higher as you get close to 1. In fact, you got a vertical asymptote there. These numbers matching about 0.685 and 0.294. Reasonably close to those. So it's good to see the numbers matching, but I also had some fun here making a visual for this transformation. So here's the X data from the uniform distribution from 0 to pi over 2. There's the graph of sine of X. X going from 0 to pi over 2. The outputs go from 0 to 1. And this will transform the X data into Y data. And it's the fact that the graph approaches a horizontal line here for the tangent line as X approaches pi over 2, that the data can get so dense near 1. And here's a 3D picture of it. Showing exactly the same thing with the PDFs of X and Y superimposed. The PDF of X is this horizontal line, that's the uniform distribution. The PDF of Y is this pink curve. Notice it's got a vertical asymptote as you approach 1. So here's the transformation in a higher dimensional space. The fact again that this graph approaches infinity as Y approaches 1 means technically speaking, the data, you might say, gets denser and denser as you approach 1. Of course, you really only see that, so to speak, when you've got, say, thousands or maybe millions of data points. Would you really see that clearly in terms of measuring density of data? Okay, so I had fun with that. I'll share that with you if you want to play around with it. Okay, I had to experiment with trying to get it to visualize it this way. But I think it's kind of neat that you can. All right, our second main example today. 2 main examples today, and then maybe some discussion about the end of chapter 7 after the second example, is a continuous convolution example. I talked about discrete convolution, and you had a take-home problem about discrete convolution in a simple setting, and I hope the example we did last Tuesday made that one not too hard to do. But let's think about continuous convolution in the context of problem number 4 in the in-class test. So here we use the MGF technique. Let X and Y be independent exponential random variables with parameter beta, which is the mean. Use moment generating functions to determine the distribution of the random variable X plus Y. So you multiply the moment generating function of an exponential by itself, effectively, is what you do. And then use the fingerprint theorem. So what you should have done, and I think most of you got this right, was to look up the exponential MGF. Exponential MGF 1 minus beta times t to the negative 1 power. X and Y they both have the same distribution and they're independent. you could write x comma y is exponential with parameter beta, which again is the mean, and independent, implies that the moment generating function of x plus y is the product of the moment generating function of x with the moment generating function of y. But those moment generating functions are the same. They're both 1 minus beta t to the negative 1 power. I'm not saying x and y are the same random variable. I'm saying they have the same distribution. Their observed values could be different though. They're modeled by the same PDF, but that doesn't mean they equal each other when you observe them. In all likelihood, they're not equal when you observe them. But they have the same distribution. They have the same moment generating functions. And there's the moment generating function of their product, which is not exponential because it's not a negative 1 power. But it does fit this one. Alpha is 2, and that's gamma. So it's a gamma distribution by the fingerprint theorem. X plus y is gamma. Not with any old alpha, but with alpha equal to 2. And beta is the same beta as before. So that's definitely the easiest way to go to figure out the distribution of x plus y. What would its PDF be, by the way? It would be this when you take alpha equal to 2. And beta is arbitrary. So the PDF of, let's call it W, equals x plus y. Would be 1 over capital gamma of 2 times beta squared. It's beta to the alpha in general. Times x to the alpha minus 1, which is 2 minus 1, e to the negative x over beta. Capital gamma of 2 is 1. So this is 1 over beta squared. 2 minus 1 is 1. There's the PDF. Oops, I should use a W instead of an X. Sorry. Yeah. Sorry, this is a W. 1 over beta squared W e to the negative W over beta. Can we derive this PDF some other way? Like the CDF method, for example. The answer is yes, but it's not easy. Let's use the CDF method to derive it. So far, I've just used the table, right? I haven't derived this. I've just used the table and the fingerprint theorem and this fact. Oops. Probability that capital W is less than or equal to little w. But capital W is x plus y. But how in the world am I going to go any further? I mean, I do know x and y individually are exponential. But usually at this point, you solve for x or y on one side of the inequality. And I mean, I could do that here, but is it helpful? Because I'd still have a random variable on the other side, not a non-random variable. We actually did do a problem like this 3 weeks ago. Remember it? with a uniform distribution, and I shaded some areas in a square to help us figure this out? Unfortunately, you can't. Yeah. Can't replace y by x and say this is 2x. We need to do something similar to what we did 3 weeks ago. Except x and y are not uniform anymore, they're exponential. And we can't just think in terms of shaded areas anymore, because with uniforms, the PDF is constant. So probabilities can be found by finding areas. With exponentials, the PDFs are not constant. But it's still going to be useful to think about areas, or at least shading regions. Draw a plane. Should I label the axes with capital letters or lowercase? Probably it's more traditional to use lowercase. What I need is I need the joint distribution of x and y. That's what I need. Chapter 5, which is the chapter we didn't spend much time on so far. I need the joint distribution. And I need the assumption of independence to help me figure out the joint distribution. And to figure this probability out, I'm going to use the joint distribution and integrate over an appropriate domain in the plane. W is fixed, say W is positive. X and Y are exponential. It makes sense to restrict your attention to where W is positive. The line little x plus little y equals W is the same as the line y equals W minus x. It's a line with a slope of -1 and a vertical intercept of W. And in fact, because the slope is -1, the horizontal intercept will be W as well. And it's this region that I need to integrate over, because that's where x plus y is less than or equal to W. And I can stay in the first quadrant because x and y both need to be greater than or equal to 0 as well. So I don't have to go down into the other quadrants. But what is the joint PDF of x and y? Our book would label that f sub xy of little xy. Independence is needed to figure it out. Remember, and I said to know this for the test in case I put a true false or multiple choice question about it on the test. And I think I did, except I wrote it in words instead of an equation. X and y are independent if and only if the joint density is the product of the marginal densities. That was a true false question written in words. And the answer was true. That's the definition of independence, not a theorem to prove. This is what independence means. And so I'm going to use that here. This is going to be independence. This will be the product of the marginal densities of x and y individually. What are those? You got to look it up in the table again, exponentials with mean beta. I hope you maybe even remember it without looking it up. It's this for x and the same kind of thing for y, except with a y. And so the joint density is 1 over beta squared e to the negative, you could write it as x plus y over beta if you like. But it might actually, for the purposes of integration, be better to write it as separately as the product of two exponentials. That might be better to write it for the purposes of integration. Either way is okay. So that's the joint density. That's the thing we need to integrate over such a region to figure out this probability. So let's do that now. For an arbitrary positive W. But just in your mind, you got to just realize W is fixed, some fixed positive number when I do the integral. Though at the end, when I finish the problem, then I say, hey, now W is a variable. Whether something's a constant or a variable is all in your head. It's all in how you're thinking about it. When you do the integrals, pretend W is a constant, then get an answer, but the answer is going to depend on W. And then you say, hey, now I'm going to think of W as a variable. So this is a little practice in multivariable calculus, actually, which is not technically a prerequisite for prob and stats. It's not, therefore, not technically a prerequisite for this course. But we do a little bit of multivariable calculus anyway. In prob and stats, we mostly try to keep our double integrals to rectangles, though I think I do, at least in class, one triangular example, kind of like this, except probably with particular numbers. W is an arbitrary positive number here. How do I integrate over such a region? It's a double integral. If, for example, I take the outer integral to be with respect to x, which is the way I usually think about it, the outer integral with respect to x, the inner integral with respect to y, write that. You always want your outer integral to be from one constant to another constant. W is a constant when I do this integral. X goes from 0 to W. The inner integral, when you're not integrating over a rectangle, is going to, in general, integrate from some function of x to some other function of x. For any, here's the way I think of it, for any fixed x, like say right there, what does y vary between? It varies along this line from the second coordinate of this point to the second coordinate of that point. The second coordinate of the first point is easy, it's just 0. The second coordinate of this point depends on x. How? That's how it depends on x. It's W minus x. That's the second coordinate of this point for a given value of x, because it's on the graph of y equals W minus x. One over beta squared e to the negative x over beta, e to the negative y over beta. If I do this double integral, that should be the CDF. And before we do it, just realize, think about it here. In the end, the x and y are going to go away. They're going to be integrated away, and you're going to be left with something that only depends on W. Do the inner integral first, leave the outer integral as is. Actually, I should be able to predict the answer for the inner integral. Should be simplified to that. The PDF of x will be the same as the marginal distribution of x. Though it's possible it could be some modification of that. Let's just see what happens. So I'm going to integrate first with respect to y. The inner integral here is with respect to y. Treat the beta's constant, treat the w's constant, treat the x's constant. Y is the only variable. So I got to integrate e to the negative y over beta. Can I do that in my head? Antiderivative. That would give me an extra factor of negative beta. Let's leave this part as is. 1 over beta squared, e to the negative x over beta. That's just a constant. Integrate e to the negative y over beta. That should give me an extra factor of negative beta because if I differentiate this with respect to y and use the chain rule, I'll get an extra factor of -1 over beta, which will cancel with that negative beta to give me 1. Y goes from 0 to w minus x. Yeah, we are going to get the w minus x involved in place of y. What will that do? Let's just see what happens. First, replace y with w minus x. Which I can bring the minus sign through and write it as x minus w. Is that worthwhile doing? To do? I'm not sure. Let's just do this initially. And then I have to subtract what I get when I replace y with 0. Does that look good? Check it over in your mind. That'll help you stay awake anyway. I think it's good. E to the 0 is 1. This is just a plus beta. I didn't try this example before class. It's turning out a bit more complicated than I was hoping, but tell me where to stop my pen. Yeah, this is multiplying times the whole thing. Yeah. Of course, the betas cancel with the beta squared to some degree. So I get really just 1 over beta. And what am I left with? I'm left with, I guess, 1 minus. Oh, this is turning out not so nice. Oh, I can bring the 1 over beta in front. Maybe I'll go ahead and do that. But it seems like I've got the integral of the difference of two things. This times 1. Yeah, okay, if I multiply this times this, I do get a little cancellation with the exponents because a plus x over beta cancels with the minus x over beta to give me 0. It looks like it's just e to the negative w over beta. If I have not made a mistake. So that's nicer than it would have been. So I'm integrating that with respect to x. And this is a constant. Hanging with me? I know it's not super exciting. The excitement comes in hoping that the answer turns out to be enlightening. But now we're trudging through all the calculation details and hoping not to make a mistake. Doing this final integral now. And again, that's just a constant. So I multiply it by x. X goes from 0 to w. Be careful. Negative beta e to the negative w over beta minus, I'll put the w in front, w e to the negative w over beta. Now plug in x equals 0. E to the 0 is 1. You get a negative beta times 1. and that becomes 0. So, boy, have I made a mistake here. The CDF, if I multiply the 1 over beta through the two minuses signs make a plus. I get a plus beta here, but then times 1 over beta is just a 1. This beta times that beta cancel. I get a negative e to the negative w over beta. And then plus or minus 1 over beta w e to the negative w over beta. This is evidently the CDF when w is positive. I'm almost done. Now differentiate it to find the PDF. And I think it will simplify nicely. I think. Differentiates to 0. I get a plus by the chain rule. This. I do need to use the product rule here. First function and second function. Derivative of the first is 1 over beta times the second. And those are going to cancel. And then I get a ultimately plus 1 over beta squared. This is looking good. Those cancel. 1 over beta squared w e to the negative w over beta. I wrote that equation 20 minutes ago. 1 over beta squared w e to the negative w over beta. Wasn't that worth it? We did the convolution to get the same answer. Of course, the moment generating function technique is easier. Although that's hiding some difficulty because the fingerprint theorem is hard to prove. This is a continuous convolution. Essentially, this final function that we got, you could say it's f star, or you could say it's f sub x star f sub y of w, where star is the convolution operator. But what does that mean? What does the convolution operator do? Let's look it up online. I'm afraid if I write it down from memory, I'll get it wrong. I do have a book that I was going to bring, that I forgot to bring, that's got it in there. Oops. Continuous convolution. Okay, here it's written as a single integral from minus infinity to infinity. For us, that would simplify to an integral from 0 to infinity. It's not obvious that it's going to give the same answer because it seems different than what we did. Yeah, and I'm not going to take the time to justify it, that it gives the same answer, but it does. Not today. Maybe when we come back. This method, though, so yeah, maybe we'll justify this when we come back from break. This method of doing double integrals over triangular regions generalizes even to situations where the variables are not assumed to be independent. Because effectively, instead of using this independence assumption, we just work with joint PDF. In that context, we're not really doing convolution anymore, but it's a similar kind of method. It's just that the joint PDF is going to have some other formula. It's the way you deal with it when the variables are not independent. You do need some kind of model for the joint PDF that you hope still seems reasonable and valid. And that's another question. But assuming you've got some joint PDF that is not the product of the marginal PDFs, you can still essentially do the same method. But this method with independence is essentially doing a continuous convolution without getting into the details about why. All right, let's just finish with a few comments about the end of chapter 7. I've given you these comments before, but I think it's worth doing again. Perhaps emphasizing the central limit theorem is the main thing worth emphasizing here. All this is related to the central limit theorem. It's certainly not a proof of it by any means, but it's related. Why? Because with the central limit theorem, we're looking at the distribution of the sample mean x bar, which is a sum divided by n, right? X bar is x1 plus x2 plus x3, et cetera, plus xn, all divided by n. The numerator is still a sum, though. And that's what we're talking about here with this example, is a sum, x plus y. It is a random sample. So the background assumption for the central limit theorem is independence of those. Random sample implies you're assuming those variables are independent. So in theory, you might think, as far as proving the central limit theorem, that perhaps what I need to do is some sort of really high dimensional convolution. I need to think about the distribution of x1 plus x2 plus ... through xn. N independent random variables, all of them having the same distribution. Do I need to do some sort of n-dimensional convolution integrals to help me prove the central limit theorem? Well, if you do, we won't do that. But I'm just saying that's one possible approach you could try to take. Imagine generalizing this picture to n-dimensional space instead of two-dimensional space. Not so clear what to do. Can't visualize it. Okay. Does this PDF have a graph that looks like a normal curve? No, it doesn't. But it does look more like a normal curve than a plain old exponential does. This will be what we end the class with today. It does look more like a normal curve than a plain old exponential distribution. Plot PDF exponential distribution with any mean you want. Actually, the number you put in here is actually not the mean. I put a 0.1 in there. That's actually a 1 over the mean. That's the way Mathematica does it. So the mean here is 1 over 0.1 is 10. There's an exponential distribution with a mean of 10. Didn't put the origin on the right spot. There we go. The sum of two such exponential distributions is a gamma distribution with alpha equal to 2 and beta equal to beta. But again, the beta here is 10, not 0.1. I think I need a 10 in here. So this doesn't look at all like a normal distribution, but this looks still not like a normal distribution, but at least it's got a hump to it. So it looks more like a normal distribution than an exponential decay does, at least. And if I was adding 3 such random variables, or 4 or 5, it would look more and more normal. And we'd be trying to visualize the central limit theorem, computationally speaking, for this example. All this theory stuff does have practical importance. Okay. These are the theory is the basis for the models. And yet after spring break, we will get into confidence intervals and hypothesis testing a bit for a couple weeks and talk about a little bit more theory related to this as well, where we see the theory is relevant. Confidence intervals and hypothesis testing is very applied. People use it in applications all the time, but you need the theory to justify what you're doing. And also to realize perhaps what to do if you're in a situation that's not a typical situation. Knowing some theory is worthwhile. All right, we'll see you after spring break.